Okay, welcome back to the new chapter, coordination compounds. Coordination compounds. Your ninth chapter of class 12. Okay, coordination compounds. So you know what is a coordinate bond from your chemical bonding, from the chapter chemical bonding. Coordinate bond is a bond where coordinate bond is something like a covalent bond where the shared electron between two atoms is completely donated by a donor atom, right? Okay. If A forms a coordinate bond with B, which represented like this, right? Okay, where A is said to be the donor and B is said to be the acceptor. Okay, so this is also known as donor-acceptor bond, otherwise known as dative bond, that you know. Okay, so we have a chapter for discussing the whole property and whole things about the coordination compounds. Okay, fine. Ready? Then, now, let me introduce what is a coordination compounds. Before that, there are actually two types of addition compounds. Addition compounds are two types. Addition compounds are two types. Two types of addition compounds. The first one is double salt. Double salt. Well, the second one is coordination compound. Coordination compound. The first one is double salt and second one is coordination compound. So there are basically two types of addition compounds, double salt and coordination compound. Then what is an addition compound? Okay, what is an addition compound means? That's a compound formed by the addition of two or more stable molecules. A compound which formed by the addition of two or more stable molecules is said to be addition compounds. Okay. For example, if I have a stable compound KCl plus I have a stable compound MgCl2, another stable compound 6H2O, when they all combine, there forms a double salt called KCl.MgCl2.6H2O, what we called as carnallite. It's a double salt, said to be carnallite. What it is? Carnallite. Okay, like that. Your coordination compound is also a addition compound. For example, I have 4KCN plus FeCN twice, potassium cyanide and ferrous cyanide. They combine to form a compound called K4FeCN 6 times. This is a special compound that you know, which is enclosed in some kind of bracket like that, okay? And this is said to be coordination compounds. Ready? Then both double salt and coordination compounds are formed by the addition of stable molecules, right? So both belongs to addition compound or molecular compound. Addition compound is otherwise said to be molecular compound, okay? Fine. Then what is the difference between these two means? If your double salt which dissolved in solvent, for example, which dissolved in water, then it completely ionized to form K plus Cl minus plus Mg2 plus Cl minus. It completely ionized and losses its identity. Okay, so write a point. On dissolving in water, completely ionized and loses its identity. Okay, then what about the ionization of a double coordination compound? When the coordination compound is immersed in a solvent, what happened means it ionized as two parts. One is a cationic part or one is a counterionic part. Okay, we will discuss the term counterion. So one is a counterion part and another one is a complex ion. For example, here the complex ion is anion. Okay, actually the identity of coordination compound is this one, the portion which is enclosed in the bracket, where that identity is still retained here, right? There is no change for that typical identity or typical structure, FeCN 6 times, right? Okay, so it is clear that on dissolving the coordination compound in a solvent, it still retain its identity. Okay, it not dissolved or it not ionized like a double salt. Okay, so that is the difference. So write a point here. Write a point here. When ionized in solution, retain its identity. When ionized in solution, retain its identity. When they ionized in solution, they retain its identity. Retain its identity. Ready? Fine. So some more examples for your double salt. Copy that. Your double salt, some more examples. Example, FeSO4 dot NH4 twice SO4 dot 6H2O. And this is said to be more salt. More salt. Okay. The next is K2SO4 dot Al2SO4 thrice dot 24H2O, and this is known as potash alum. Potash alum. Okay. No need of writing examples for your coordination compound because the chapter is completely based on what? Coordination compound. Okay. So that's a difference between a double salt and coordination compound. Okay. A double salt which retains its identity, whereas a a double salt which loses its identity in solution, but a coordination compound still retain its identity in solution. Okay. Where both are belongs to addition compounds because they are formed by the addition of stable molecules in a typical pattern. Okay. Ready. So the next concept in your coordination compounds, that is some important compounds. Some important, it's not compound, some important terms. Some important terms are there in your coordination compound. For example, let the coordination compound is like this, Ml6, okay, Ml6 E3. Ml6 E3 like that. Okay, where M generally said to be central metal atom, central metal atom, or otherwise it may be ion. Where L is known as ligands, you know. I'll explain what are they, ligands. And generally anything which present outside of the coordination sphere or coordination of this bracket, that is said to be counter ion. Counter ion. This is the basic general parts of your coordination compounds. Okay. So we will explain the whole. Ready. So write down number 1, central metal atom. Central metal. That's enough. No need of atom or ion. Central metal. Okay. Write a point. They are atom or ion. They are atom or ion. They may be either a neutral atom or maybe ion. They are atom or ion, to which a fixed number of groups are arranged by, we know that these ligands are arranged around the central atom in a particular geometry, what we call as its shape. Okay, like your shape in your shape based on valence bond theory, say tetrahedral, square, planar, like that. Okay, so these all are atom or ion. So they are atom or ion, to which a fixed number of groups are, where the groups are said to be ligands. Fine, we'll explain the term ligand, to which the fixed number of groups are attached by or bounded by coordinate bond, to which a fixed number of groups are bounded by coordinate bond. Okay, so write some example or give one or two example. Okay, listen. For example, If I have the coordination complex K3FeCN 6 times thrice, and if you know how to find the oxidation state of this central atom, we will explain how to find the oxidation state of the central atom. Where here the oxidation state of Fe is 3 plus. So here the central atom which exists as Fe exists as what? Fe exists as ion. This is central metal ion. Central metal ion. Okay. Or here the charge of Fe is 0. So here the Fe exists as what? It exists with a 0 charge. So that's a central metal. That's a central metal atom. So either it may be an atom or it may be an ion. That depends. Okay, depends on the net charge or residual charge. Anyway, this is said to be central atom. Ready? Fine. Move to the next term. The next term that is very important. The term is ligands. Ligands. Ready? Fine. Ligands. Ligands are what? Ligands are either atom or ion. Okay. Either it is an atom or it is a group of atom. Okay. Fine. Either it is atom or molecule like that. So ligands are atoms or ions or molecules. Atoms, ions or molecules. Atoms, ions or molecules. Okay. Sorry. Usually molecules are ion. No need of atoms. Okay. Ligands are molecules or ions which are bounded to central metal atom by coordinate bond. So these pieces are bounded to the central metal atom by means of coordinate bond. Okay. So they are atoms or ion which are bounded to central metal atom by coordinate bond. Okay. Fine. So they are said to be the ligands. Okay. For example, if I have a coordination compound CrH2O 6 times Cl3, where the ligands are water. So water is a neutral molecule, right? So this is a ligand neutral molecule. Ready? For example, if I have a molecule like this, where Cn minus is the ion, this is an ion, polyatomic ion. This acts as the ligand here. Okay. So the ligands are either neutral or ion, or it may be positive or negative ion. That depends. Fine. Okay. Positive ligands are also there. Positively charged ligands also there. Okay. We'll explain that. So these are said to be ligands. Fine. So write some examples. The next, denticity. That's a very important point in your ligand. Denticity. So denticity have some kind of relation with your denticity, with your teeth. Okay. Which means how much coordinate bond that can be offered by a particular ligand, that is said to be denticity. If I am a ligand, then how much coordinate bond can formed by me to the central atom, that is said to be denticity. If I can form only one coordinate bond, then my denticity is 1 and I am said to be, or me is known as monodentate or unidentate ligand. Monodentate or unidentate ligand. Ready? If I can coordinate to the central atom by means of two different teeth or two different portion, then my denticity is what? 2, and said to be bidentate or didentate ligand. If I can if I can bond the central atom by means of three different donor atoms, we know that ligands have some kind of donor atom. Here the donor atom is oxygen. Here the donor atom is carbon. Okay. So there is some kind of donor atoms where the electron pair is existing and that have to supply to the central atom. Ready? We know that there is a bond between central atom and ligand, right? And that bond is what? Coordinate bond. Where the complete 2 electrons for that typical coordinate bond is given by your ligand. So ligand is a donor atom, right? Ligand is a donor, right? So if a ligand can donate, or if a ligand can act as, if a ligand can donate 3 different electron pair at a time, then its denticity is 3 or tridentate ligand, like that. Okay. So that is the term what we call as denticity. That's very important. So define that. It is a number of ligand donor atoms It is the number of, simply donor atom is enough. It is the number of donor atoms which present in a particular ligand. It is the number of donor atom which present in a particular ligand. Okay. So now we can discuss different types of ligands based on their density. Moreover, their names, structure, and Hall properties. Okay, that's very important. Ready. So now the next is your ligands based on the density. Okay, very important. So you want to study the charge of ligand and also the names. Okay. So the first one, that is monodentate ligand. Monodentate or unidentate ligand. You know what is the density? You know what is density? So here the density is 1, which means a ligand can donate only one, or a ligand can donate by means of only one donor atom. Okay, so that is said to be monodentate or unidentate, like that. Okay, so here the structure of that particular ligand. Here we have the name, and here we have the charge. Okay, so the first one, let me start with the neutral ligand. Neutral ligands: H2O, NH3, CO, CS, NO, PH3, PH3 twice, pyridine, okay, I'll extend the space to the top. Okay, fine. So now this is enough. I'll give you more. So these all are neutral ligands. First one called aqua, water. When it is a ligand, it is called aqua with a charge 0. Okay, these all are neutral. Ammonia, that is said to be amine. When the ammonia is ligand, then it is said to be amine. Charge is 0. CO, carbon monoxide. When it is a ligand, it is said to be carbonyl. CS, thiocarbonyl. NO, nitrosyl. PH3, phosphine. PH3 thrice. You know, this pH is phenyl. So these 3 hydrogen replaced by 3 phenyl. So this is triphenyl phosphine. If here is 3 hydrogen, then it is simply phosphine. If here there is 3 phenyl group, 3 benzene ring, then it is said to be triphenyl phosphine. Triphenyl phosphine. Is it okay? All these have same charge, 0. I'll give you more. Listen. The next neutral ligand, that is pyridine. Okay. Pyridine. This one. Okay. Pyridine usually abbreviated as PY. So this is said to be pyridine. So the charge is 0. And CH3NH2. We know methylamine. So these all are the important neutral monodentate ligands. Okay. So let me check the charged monodentate ligands. Okay. Charged monodentate ligands. Fine. Listen. The very same table, but it is charged. Cl minus, Br minus, I minus, F minus, H minus, OH minus, okay, O2 minus, O2 2 minus. The next is NH2 minus, NH2 minus, N3 minus, N3 minus, a lot of them also there. Okay, listen. So now you need to find this, study this, okay. Cl minus. Actually, the name of Cl minus is chloride. So here it is chlorido. When it becomes a ligand, it either ends with the suffix of IDO or ITO. IDO or ITO, chlorido. Well, the charge is -1. Br minus, bromido. Well, the charge is -1. I minus, iodido. Charge -1. F minus, fluorido. Charge -1. H minus, hydrido. Because H minus is said to be hydrate, so that's become hydrido. OH minus hydroxide, so this become hydroxido. O2 minus oxide, so this become oxido. O2 minus peroxide, so this become peroxido. NH2 minus amide ion, so this become amido. NH2 minus amido. NH2 minus become imide ion, so this is imido. Ready? NO3 minus or NO2 minus. NO2 minus is actually nitrite ion, so this become nitrito. And there is another pair, ONO minus. NO2 minus is said to be nitrito N, and ONO minus is also isomer. That's also nitrito, but that is nitrito O because the donor atom is oxygen. Here the donor atom is nitrogen. Okay. These all have, sorry, -1, -1, -1, -1. This half -2 charge, this half -2 charge, this half -1, -2 charge. Or the charges are given in the top. Okay, so you can complete that table. Okay, what is the charge of that ion? That's exactly mentioned in the top of that ion. Okay, fine. So I'll give you another. Ready? That is NO3 minus nitrate. So this is nitrato. SO3 2 minus sulfato. Okay. SO4 2 minus sulfate. This is sulfito. This is sulfate become sulfato. CO3 2 minus. Okay, CO3 2 minus. This is carbonate become carbonato. S2 minus. This is sulfide become sulfido. Okay, sulfide become sulfido. Ready? Next. The next is N3 minus. Nitrate ion, nitrido. Okay, like that. These all are simply said to be monodendrite ligands, but there is a charge. The next is Cn minus, cyano or cyanato. Next is Nc minus, isocyano or isocyanato. isocyanato. The next is S CNS minus. Okay, thiocyanato. For the donor is sulfur. Okay, and the next is NCS minus, isothiocyanato. Okay, these all are generally monodentate charged ligands. Ready? Some positively charged ligands also there. For example, NO plus, nitrosonium. The name is nitrosonium. For the charge is +1. NO2 plus. The name is nitronium. Nitronium. Charge is +1. We know NH2 is what? NH2 is hydrogen. So when it absorbs NH plus, here is the donor atom. And this is said to be hydrazinium. Hydrazinium. Where the cationic ligands are ends with a suffix of IUM. Okay. So these all are simply the monodentate ligands. Ready? Monodentate neutral, monodentate charged, negatively charged, positively charged, etc. Ready? So now we can discuss the bidentate and polydentate ligand and some special type of ligands like ambidentate ligand, flexidentate ligand, chelate ligand, etc. Okay.